first. Now we'll share. All right, so we're going to talk about chapter 5, which is least squares regression. So chapter 4 really kind of was the preliminary step. If you think that there's a good correlation, the next step is to go to the regression line. So the regression line is a straight line that describes how the response variable y changes as the explanatory variable x changes, and it's often used to predict. So the idea here is, let me draw a quick little scatter plot here. I just want thing. Okay, so I've got my scatter plot here. So I've got my explanatory or independent variable down here, and I've got my response or my dependent variable here, and I'm going to have a bunch of dots. Oh my gosh, I cannot work the keyboard today. So I've got my these are my things. Okay, so we can see here that I can draw a line here. Now there's a lot of different lines I could draw. I could draw something, any of these, right? So the question is, which is the best line? And so the answer is, okay, the line that we draw, we could draw a line that minimizes the horizontal distance to the line. Okay, so that's one thing we could do. Or we could draw a line that minimizes the vertical distance, like this here in green. Or we could draw a line, pink maybe, that minimizes the orthogonal, or you could think of this, if I took this pink is, it draws the orthogonal or a right angle distance here to the line. Okay. So the question is, which is best? And so with OLS regression, ordinary, ooh, I don't want to use pink anymore. Ordinary least squares, which we often just call OLS. The best line minimizes the vertical distance to the line, which would be the, well, you can't see here because I changed my colors, but it's the green distance here, or it's pink in this one. I didn't mean for it to be. Let me draw that one back in green. It minimizes the vertical distance of all of these, okay? So there are a lot of different methods, and all I'm going to tell you is the best method, and we're not going to get into the math here, but the best method minimizes the vertical distance to the line. Now, if you take my Math 2040 class, I will actually do a little demonstration to show you that, but I'm not going to do that because it takes way too long. And anyway, so we call it least squares or ordinary least squares. It's the most common method. It minimizes the vertical distance such that it always passes through the point X bar and Y bar. So you're probably all familiar with the equation from Math 1010. Let's say y equals mx plus b. Correct? You've all seen that many, many times in previous math classes. Okay. So the idea here is, instead of using that, well, I prefer that because I think that's what you guys are familiar with. I think in the book sometimes they do y equals b0 plus b1x, or sometimes they flip those around. I think that's terrible notation, and so I'm going to go back to the y equals mx plus b, because that's what you guys are generally familiar with. Okay, so so my equations, dang it, I'm trying to box that. Oh my goodness. Do not know what's wrong with me today. I want to box that. I didn't even do it very well. That's the equation that we're going to use. And in fact, if you look at the formula sheet, I'm going to use that instead of this other equation, because most of you are familiar with this equation here. So now the question is, how do you find M and how do you find B? Okay. So I guess, yeah, that's what they have in the book. So your slope is given by your correlation coefficient times your standard deviation of y divided by your standard deviation of x. And your y, or your y-intercept, which is b, is going to be y bar minus mx bar. Okay. So remember, it's important to keep predictions in range. But a lot of times, the example that I like to give, you know, babies actually grow really fast. And so the idea here is, if we were doing a growth curve for babies or people by age, what'll happen is, if we did it for babies like this, you know, if this was between, say, 0 months to say 36 months. 36 months. Okay, I'll just abbreviate K. It might be really, a straight line might be a good thing for that. But the problem is, if we continued, and I'll use a different color for this straight line, if we continued this growth pattern forever, maybe this is, you know, maybe this is 20 inches, a typical baby, and then when they get to 3 years old, maybe they're 40 inches, let's say. And the problem is, if you kept going on here until they were, say, you know, 20 years old, and obviously I shouldn't be switching my scales on here, but I'm just trying to illustrate a point, it might show that they're 9 feet tall. And so the idea here is, it might be linear from 0 to 3 years, and that's fine to do prediction within here, but you probably shouldn't be predicting it out when you get out to 20 years old, because then they're going to be 9 feet tall. Okay? Because really, in reality, what happens is the growth curve is going to go off something like this, and it's going to have a different slope. Okay, so let me pull up this worksheet here, and we're going to do an example.
Professor Bennett, just out of curiosity, do you have any hard, fast rules on how far you can do your predictions outside the range of the data that you already have, or do you keep it inside that range at all times?
You can go outside a little bit, but not a lot. So, okay. And I don't have a so using that example, if I were to, there we go. Oh, I found it. If I were to use that for the growth curve for the infants, if I went to maybe 3.5 years, that would probably be okay.
Okay.
That's a little bit outside the range, but it's probably okay for that. But I wouldn't want to go out to 8 or 9 years or 10 years because the growth curve is going to change. And it really should be more of a curve than a hard point like I've got on this. So, all right, so let's do an example here. A golfer has chosen to swing a ball on a 70-degree day with no wind. You want to see if there is a relationship between club head speed and the distance in yards. So let me ask you guys, first of all, do you think this would be a valid experiment to be doing? Does it make sense?
As a golfer, yes, but I know that there's other details involved, such as launch angle and things like that. But yes, it is valid.
Right. Yeah. Okay. So what would be the first step that you would do on a small data set like this?
Make a scatter plot.
Make a scatter plot. It's a good thing I had that right there. I gave away the answer. All right, so insert, we're going to do a scatter plot because, so would you agree here, if we label this properly, if this is club head speed, club head speed in miles per hour, and this is distance in yards, would you agree that it seems like linear correlation is a good idea? Okay. All right. So I think we would all agree with that. Now, the question is, we could calculate the correlation coefficient. I'm going to do this really quickly because I don't want to spend a lot of time on correlation coefficients because we did that last time in class. But I do need my correlation coefficient. The idea here is I get a correlation coefficient of 0.9387, okay? And so now, so that seems like, let me see here, somebody besides Wes or Easton, is that strong, moderate, weak, or no correlation? Am I gonna have to start picking on people? Elise, would you say, based on this correlation coefficient here, strong, moderate, weak, or no correlation?
That looks like a strong correlation.
Strong because?
Because the line seems to be straight.
Okay, and what else? How do you decide between strong and moderate? Do you remember the rule I gave you last time?
No, I wasn't in class last time.
Okay, who remembers the rule? So you will want to remember this rule. Allie, do you remember the rule?
So there are certain like numbers like that it has to be in between to be like strong or weak or moderate.
Right.
And the closer the numbers are, I don't remember exactly what I remember what the moderate ones are. I don't remember which numbers they are for it to be strong.
Okay, what's moderate?
It's like 0.3 to 0.7. Is that what it was?
Okay. So 0.3 to 0.7 is moderate, so greater than 0.7 would be strong.
And less than 0.3 would be weak.
Weak. And close to 0 would be no correlation. If it's supported by a scatter plot. So remember, if I had a curve in here, I might get a correlation coefficient of 0, but that would not be appropriate because we're assuming it's a straight line. And if it's a curve, all bets are off. Okay, so you did remember. Okay, all right, so we said strong. So remember that. You'll need to know that for the test. So remember those values. 0.7 is strong, 0.3 to 0.7 is moderate, less than 0.3 is weak, and then close to 0 is none. Close to 0, and there's no pattern on this scatter plot. Okay? All right, so now the question is, we need you to come up with the regression. Find the regression equation. Okay? So there's two formulas that we're going to need to use for that. Let me pull those up here. I wonder if I can copy both of those. Is that going to let me copy? Oh, it worked pretty well, surprisingly well. Okay. So these are your two things. Okay, so I've already found the correlation coefficient. I need the standard deviation of both, and I need the mean. In fact, the funny thing is, if you're calculating the correlation coefficient, you're going to need these anyway. But I hope that whenever you guys get a data set, that you immediately just calculate the mean and the standard deviation. Just automatically. Okay. Okay, so the idea here is if I find the slope m, that's going to equals the correlation coefficient, which I cheated and found it that way, times the standard deviation of y. So we're saying that yards is the dependent or response variable, speed is the independent or explanatory variable, divided by standard deviation of x. And then I'm going to say that the y-intercept, or b, equals y bar, which is that one there, 266.75, minus the slope that I just found, times x bar, which is that number there. Okay? So once I've found those two equations, now I'm going to say that y equals m, and m is 3.1661x plus the negative, negative 55.797. Okay, so that's the regression equation. Now, I will tell you, if you're using Excel and you want to check your answers, you can add a trend line to this thing here. Now, really quickly, I don't want to spend a lot of time on this. One of the interesting things about Excel, you can do a straight line or linear, which is what we want. You can also do exponential or logarithmic, and you'll see that the curve doesn't really change very much. Or moving average, then that looks kind of goofy. But at any rate, you can draw a straight line here, and also you can display the equation, which is right there. So that equation is the same equation we got here. Okay? So that's kind of cool. Now, let me go back to my notes here for a second. So essentially, if I give you a data set, so on this is the kind of test question I could ask you. I could say draw a scatter plot, which you'll draw. Then I could probably say find the mean and standard deviation, which you should do. Excuse me. And then I could say find the the equation for the slope and the y-intercept, and then this is the ordinary least squares regression line. So, and you can see that matches that. So, do you guys feel comfortable and confident doing that?
So with that equation and with that information, so then you would be able to make a prediction as far as what your distance would be at like a club speed of 104, since you don't have that a data point there.
Yeah,
is that generally what you'd be using this for? Or?
You could use it for there. You could probably even go out to 106 and 98 without too much problem, but I probably wouldn't go crazy here. Now, the interesting thing is, just for fun, okay? So let's pretend, for example, just to prove to you that you should not go outside the range. So how far would ball go if I hit it at 0 miles per hour? Okay. Now you know how far it would go. It would go 0 yards, right? So basically we're saying don't hit the ball. But according to this equation, how far would it go?
Negative 55.797 meters.
Yes, it
backwards.
would go backwards 55.797 yards. Okay. So hopefully that would be proof right there. That prediction outside the range is a little bit risky. In fact, even if you used, say, 20 miles per hour, so the idea here is I would take this times 20 plus the negative, whatever that is. So if I hit it 20 miles an hour, do you think it would go just 7.5 yards? No, I'd probably go farther than that, right? So remember, this is really good. If your cloud head speed is between 99 and 105, maybe you could get outside that range, 98 and 106, and you'd probably be okay. But if you go way outside the range, like, 0 to 20, I'll bet you it would go a lot more than 7.5 yards. So, so that's what we mean when we say prediction outside the range is risky. Okay. All right. I can't remember what this link is. Oh, you don't really need to know this. This talks about residuals. Well, it does. Actually, this is another thing that I should probably mention here. Now, the interesting thing is, well, maybe I'll do it this way. Let me back up a second. Now, you can see here twice one time we hit it 100 miles per hour, and it went 257 yards, and another time we hit it 100 miles an hour, and it went 263 yards. And so that's these 2 points right here. So according to my chart, if I looked at it here, I would predict that it would have only gone 261 yards. So you golfers out there, such as Allie, okay? Allie, do you golf? Allie, you're on mute, or we can't hear you.
I do golf with you. Sorry.
Okay. So why do you think it went farther one time and shorter another?
Well, depends on how you hit it. If you get under the ball or if you top the ball, or there are lots of factors that go into it.
Okay. So your angle there, what might be some other natural factors that would affect it?
Natural factors like the wind.
Wind. It says there was no wind, but maybe one time there was a little gust of wind that pushed it farther or pushed it back, right?
Yeah.
Could be either direction. Anything else?
Also how deep your ball is in the grass. Like if you're in like a tough spot, that could affect it because it has like some resistance when you first hit it.
Okay.
Like if you're in the sand or if you're like in a rough patch.
Okay. If you hit it in the sand, it might fall backwards or forwards,
Yeah.
probably backwards.
And also if like the ground is slanted, it might roll back or bounce off of a rock. You never know.
Yeah, it could bounce off a rock. It could hit a wet spot on the grass. So there's lots of things. And so the distance between the line, the vertical distance between the line and the point, that's what we would call the residual. And so anyway, we won't get into that too much, but the idea here is if you have either an outlier or an influential observation, and so we could have that. What if, here I'm going to insert a point here. What if we hit it 150 miles an hour? Wow, you can already see that that really changed things. And it went 300 yards. Okay. Now, do you see? So here's what I'm going to mention here. You see here, clearly this is an outlier. It's an outlier, not both in speed and distance. But the regression line, well, this is what we had before here, okay? You can see that the equation has changed on my chart. And you can also see this line doesn't really match the majority of the points anymore. And so an outlier is going to be, and it doesn't necessarily have to be an outlier, but this one is in both cases. But it's going to make the line come closer to it. And so we would refer to this as an influential observation. And so if I remove that point, you can see, once again, it changes there. Now, the other point that I want to make here, let's say that it went 108 miles an hour. So, and then this was going to be 290, let's say. So you can see in this case, we've changed this, so 1 point can make a big difference. You can see that it still follows the rough line here, but now we can see our slope is a little bit higher than it was before, and that's also a lot higher. So now if it's 0 miles an hour, we're going to go backwards 86 yards. So even though, so we would still refer to this point out here, 108, as an influential observation. If it was 500 yards. Okay, now it's clearly an outlier. We've really changed this. And if I change this to, let's say 90. Okay, that's clearly an outlier. In fact, the line doesn't even match. You see that the line is negatively sloped, even though most of these are positively sloped. So so outliers can have a huge impact on your data. And so the idea here is you generally like to avoid outliers when you're doing this because it's going to have a big impact on your regression line. So does that make sense? Now, let me just mention one other thing. I used to teach this class at BYU, Idaho. And one of the things that they used to do, it was kind of interesting, is apparently somebody was digging in the desert in Africa and they found a crocodile head that was all they found was the head. They didn't find any of the rest of the body, only the head. and they found a crocodile head that was 6 feet long. Okay, it was huge. And they were trying to figure out, because they didn't have the rest of the body, how big that crocodile was. And so they used regression. So this film would take 2 hours. It would have been nice to just have a short version of the film, so people didn't have to spend 2 hours watching it. But what they did was they wanted to figure out what is the head length versus the body length of crocodiles today. And so they took a lot of caimans and all the different kind of crocodiles. So anyway, so what they did was they extrapolated out, and we did say that prediction outside the range is risky, but if this dinosaur crocodile matched current crocodiles, how long do you think it would have been? Any guesses? I'll let anybody guess.
40-footer?
40 feet long, that's exactly right. So did you watch the movie or something?
I remember reading an article about it.
Yeah, they call it Super Croc. The funny thing is on that stupid website, it was a National Geographic website, and if something happened to your internet and you tried to like restart the video, it would always start at the beginning, and it was so annoying. But at any rate, yeah, they tried to make a model of this crocodile that was 40 feet long. It was so huge. I can't imagine. But even in that case, you would say, so my point is you have to be a little bit careful. Now, number one, if you're finding a 6-foot crocodile head, it's not like, clearly it's an outlier, but you're trying to do your best, and so it was the only specimen they had. So prediction outside the range is still going to be risky, but we would probably expect that it wouldn't just be this all head and no body crocodile. But I guess it could be, you never know. Number one, but number two, they use regression. And so it could be that sometimes your influential observations, I had a teacher and she once said that sometimes your outliers are your Nobel Prize points. So anyway, let's see here. Okay, so let's do some examples here. So here, let's do it this way to hopefully give away the answer. Let me do a few other things here. So use the equation of the least squares line to predict the humerus length of a fossil with a femur length of 50. So the idea here is we're going to take the humerus length is going to be negative 3.66 plus 1.197 times the femur. So how would you use that equation? Let's see, I picked on Allie. So Bridger, I hate to ask because you're usually not going to answer. Are you here, Bridger? One of these times, Bridger's going to surprise me. Easton's already participated. How about Janie? Janie, could you tell me what to do how would I figure out the length of a humerus based on a 50 centimeter long femur?
Weren't we supposed to create a scatter plot first, just based on the last example we did?
Okay. Well, what I'm saying is the scatter plot's already been done, and this is the release squares regression table, and so we're assuming that this is already okay.
Oh. Then I have no clue what I would do.
No clue?
This. Yeah, I have no clue.
You're going to be like, oh, that was way easier than I expected.
Oh, I'm sure I will be, because that's usually how it goes, but it's fine.
Okay, so here I'm going to give you one more clue here. The femur is 50 centimeters long, I'm going to plug it into this equation somehow.
Oh, so we just multiply.
Ah, there we go.
50 centimeters.
Tell me what
Okay,
to
yeah,
do.
that was way
So the
easier.
humerus equals what?
Um, $63.51.
Oh, you just figured that without telling me what to do. How do I do it?
Oh, sorry. So you multiply 1.197 times 50. And you get 59.85, and then you would add negative 3.66.
So that minus 3.66. Okay. So, oh, because I got 56, you got 64, you said.
Yeah, I didn't notice the
negative.
Yeah.
Okay, yeah, so don't forget the negative, okay? So you would expect a humerus bone to be 56 centimeters. Okay? So that was nice and easy. You'd probably like that question on the test, right?
Yeah, can we do a lot of those, please?
Yeah, that's not too bad. What if I said I found a 70 centimeter humerus? I have a corny joke in here. Let me see if I can find it. You may not think it's funny, but I found this humerus. But I'm bump. No,
That
no,
took me a while, but I got
okay.
it.
All right. So since Janie did that, how about Yami? Are you here?
Yes.
Okay. So can you use this equation to find out how long the femur is?
Yeah, so we would do 70 times 1.197 plus negative.
Okay, now remember this is the femur length. So so we gotta be careful with this. So it's gonna be 70 equals, right?
Yeah.
70 equals
Negative 3.66 plus 1.197 times 56.19.
no, we don't know how long it is. So I'm gonna put F for femur.
Okay.
I'm still going to put F for femur, and I'm going to put this. Okay. So now, okay, so we're using this equation backwards. So how do I solve for F?
I'm not sure.
Do you want to phone your friend Elise?
Yes.
And Elise is saying, you're not my friend anymore if you're phoning me. No, just kidding. Elise, you got any ideas? How would you solve this? You're still here, aren't you?
No, I have no idea.
No ideas?
Mm-hmm.
Oh, it's just a little bit of algebra. Somebody must be answering that because I heard myself in a horrible echo. So you can answer, whoever that was.
Wouldn't we add 3.66 to 70?
Yes, you're going to add 3.66 to both sides. Just doing that, 3.66 to both sides. So this is going to be 73.66 equals 1.197 times the femur length. And then what?
You divide both sides by the 1.197.
All right, we're going to divide both sides by 1.197. So this is a little bit of algebra. F is going to equal 73 divided by 1.197, which works out to be 61.53718 centimeters. Okay. So we can use it both ways, assuming this is a true relationship. Okay. Any questions on that so far? Okay. All right. Now, let's see here. So in our class, we're going to focus on linear or straight line regression. Just as a reminder, regression can be misused. Straight lines don't always fit the data very well. Other curves may fit better. So some examples here, we've got, this is from Wikipedia. So you can see a curve might fit the line better, or in this case, yeah, you can kind of see that a curve kind of might fit that line a little bit better as well. We're not going to focus on these other types other than to know that they exist. I'm not going to ask you to find that curve because that's more complicated. You can also have polynomial regression, something like that. We're not going to do anything that complicated. I just want you to know that they exist. And you're probably breathing a sigh of relief that I'm not going to say find that curve. Wow, that's some crazy stuff. Logistic regression, that's another thing that you can do. Now, logistic regression is kind of interesting. Typically, you would use that when you would, oh, so this is another kind. This is what we kind of call an S-curve. So they use this for logistic growth of a population. We're not going to do anything like that, but just know that basically there are other types of regression that exist. Now the question is, sometimes we want to know how good our model is, and what we can do, let's go back to the golf one that we did earlier, okay? And so I asked earlier, was it Janie, were you the golfer?
No, that was me, Allie.
Oh, that was Allie. Allie was the golfer, okay. Janie, are you a golfer?
I am a mini golfer.
A mini golfer. So you don't like you do like mini golf, not real golf, okay?
I've
hate
never
golf.
real golfed.
Yeah, you've never real golfed? Oh, I have. It's still a boring sport, but anyway. So Allie had mentioned, so you know how the ball hits the club, or it might hit a rock, or maybe there's a wind, or maybe there's a little soft patch, and so there's always going to be some variation that goes on here. And so one of the things that we can do is we can say how good or how well does the model fit the data, okay? And so what you can do is you can just do what we call the R-squared value. Now, everywhere that I know, they just refer to it as the R-squared value, and you just simply take the correlation coefficient and you square it, okay? Now, and so the idea here is you're going to get a decimal between 0 and 1, okay? So what this tells you in this case is that basically 88% of the variation is explained by the model, and then you can write the equation y equals 3.11661x minus 55.797, okay? So this one seems like it fits the model pretty well. So 88% of the variation is explained, 12% is unexplained, hitting a pebble or a wet spot or a gust of wind or something like that, okay? So 12% is unexplained. Okay. And so that also, only in a statistics book do you know that this is called the coefficient of determination, which I think is a terrible name because nobody calls it that except for authors of statistics books. Most of us just call it the R-squared value. So you would say, based on this data here, if 88% is explained, that's a pretty good model. Okay. And so that's what we're going to call the thing. So now the interesting thing is if your correlation coefficient is 0.7, your R-squared is going to be 0.49. And so we remember we referred to this as strong correlation, 0.7. That's kind of the limit there. But even with strong correlation, you're only going to get half of the variation explained. So that's kind of interesting. Now the question of causation. So it seems like how fast you swing the golf club should affect the how well you, or how far the ball goes. That seems like a plausible explanation. But remember that a strong relationship does not necessarily mean that change in one causes a change in the other. The relationship between two variables is often influenced by other lurking variables. The best evidence comes from randomized comparative experiments. And remember that observed relationships may be due to direct cause, a common response, or confounding. And so the idea here is, even though a relationship can be used for prediction, the observed relationship can be used for prediction even if it's not the cause. So you'll remember last time when we were looking at this, I showed you the video about polio, right? Polio. Did anybody watch it? Nobody watched my video. It was only a minute and a half long, but here's what I want to do, okay? As we look at this video here, okay? Now this is another example of a nonlinear correlation. But the idea here is between the months of June and July, you could use this line here, the ice cream sales, to predict how many polio cases there would be. Even though ice cream has nothing to do with polio. Okay, so so we can still continue to use those relationships even though they may not have anything to do with them. So does smoking cause cancer? They were highly correlated for a long time, and we could definitely say now that smoking causes cancer. Okay, there's a strong association between the number of people who own handguns and the homicide rate. So this is another example that, yeah, it would make sense that these are associated. But here's an example where nations with a high number of TVs have a higher life expectancy. So does that mean that if you give nations televisions, like in Africa, they don't have very many TVs, so we're just going to give them a bunch of TVs, is that going to improve their life expectancy? Does that make sense? You think that's true, Easton?
Yes, it makes sense, but it's not true.
Yeah, so the idea here is nations with a high number of TVs do have a higher life expectancy, but shipping a bunch of TVs to Africa is probably not going to help their life expectancy, is it? Okay.
Probably not, because the things that are lowering the life expectancy are still there.
Right. So is there a lurking variable? Yes, and so the lurking variable is wealth. So people with good health insurance have better life expectancy. And so they don't have health insurance in Africa. And so shipping a bunch of TVs there, so the number of TVs does not, so there is a correlation because TVs really is a proxy for the wealth of a country or maybe the health insurance of a company. So this would be an example of a nonsense correlation. So I wish there was a way. There's another video I want to show you guys here. And I know you can't hear it, so I'm going to narrate this because I know you can't hear it. Maybe I will post this, and you guys should really listen to this, but the idea here is, this is another Freakonomics video. So, okay, so this is Stephen Levitt. In fact, here's a picture of him over here. This is Stephen Levitt. He came up with this really interesting thing, and what he said was that in 1973, the United States legalized abortion. And he believes that that had an impact on crime 20 years later, which is a very strange idea. And it's one of his most famous things. So the interesting thing about this is, I'm going to send you guys this link because I think it's really interesting. There's actually an updated episode where he has found more evidence his hypothesis is true. And so what he did was compared the crime rate in the United States versus the crime rate in Romania. So Romania was really an interesting country. You've probably not heard too much about it. But what happened in 1968 was Romania outlawed abortion. So it's an interesting difference where you take the United States, which legalized abortion, and then 5 years before, Romania legalized it. So one of the things that he did was he looked at the crime rates in Romania and they just skyrocketed 20 years later. And I'm missing part of this. Yeah, there's a part of this video that I'm missing. I wish I had the real Freakonomics one. This is pretty good, but this takes place after what I want, the Romania part. But let me go back to this graph here. I wish they had this. So one of the things that he found, they were trying to come up with some ideas. Why would the crime rate have gone down? And so one of the things that he found was let's see, there was, gosh, why can't I remember? I wish this was on Netflix because there's part of this video that we're missing. But I know that gun control was one of these pieces of the pie. More police present was another piece. Oh, it was decreases in the crack market. Crack was really associated with a lot of violence and a strong economy. So anyway, that's basically what this side of the pie graph looks like. And so these reasons here account for 55%. And so basically what we're saying is 55% of the reasons that crime decreased in the 1990s was due to increased police presence, longer prison terms, better economy, decreases in the crack market, and gun control, which meant that 45% was unexplained. And so the interesting thing about this video is Levitt tries to say, okay, well, we know 55% is explained, but why isn't the 45? So that 55%, these are the R squared values, okay? And so even with all of those, you'd say that 55% is a little bit more than 0.7 as your correlation coefficient. So he's trying to come up with a reason why the crime rate went down, and we've got 45% that's unexplained. And he's trying to make the case that legalizing abortion was the reason. And so the first thing that he says was there were 5 states that legalized abortion before the rest of the country. So those are the red states that he's got this there: Alaska, Hawaii, New York, California, Oregon. So he compares the crime rate between where it was legal versus easily available, and he can see that the places where it was easily available had a 30% drop in crime versus just the states where it was legalized. And so he also noticed that people under the age of 25, okay, so people under the age of 25, they had a lower crime rate than people over the age of crime rate. And so this is 25 years after Roe v. Wade, basically. And so he thinks that gives evidence. So the idea, once again, is he's using correlation. He hasn't found. This is a really hard thing. It's not like you can randomized controlled trial. Actually, you can see. Okay, so these are the things. So prison increase accounted for 30% of the drop in crime. Crack decrease accounted for 15%, and then strong economy, police increase, and other reasons such as gun control were the other 10%. But 45% was unknown. So at any rate, so this is kind of an interesting video, kind of a little bit controversial, because it's not, this is something you can't really test. As I mentioned before, it would be unethical to force some women to have abortions and force other women not to have abortions. And so it's not anything that you can really test. And this is one of these cases. Levitt says sometimes you have to rely on these natural experiments. And so that's why he compares the United States versus Romania, because in Romania, the crime rate just skyrocketed after they legalized abortion. So it's the best since we can actually test that. So let me see here. Is there anything else? Oh, I do have that there. Okay. So another thing I just want to point out here, remember we can't always do randomized experiments due to ethical reasons. And so kind of the criteria for establishing causation is, number one, the association has to be strong. And so smoking and lung cancer would be an example. In all the studies they ever do, smoking and lung cancer are always associated with each other. The association is consistent. It's been seen in multiple studies. Higher doses lead to stronger responses. So using smoking and lung cancer, people who smoke bore and have a higher dose of smoking get lung cancer more often. The cause predates the effect. You have to smoke for years before you get lung cancer. And the cause is plausible. So they've done animal experiments to show that it causes cancer, because it is ethical for us to force rats or monkeys or whatever to breathe smoke. We just can't do that to humans. So, are there any questions you guys have on chapter 5? Okay. I'm going to take that as a no. So, now the question I have is, I'm done a little bit early today. What we can do, let me ask you guys what you think about this, is we can keep going. I was going to cover chapter 12, and we can, because we're going to skip some chapters now. Remember, we covered 8, 9, and 10 already. And I normally would jump to chapter 12 today anyway. We can start on chapter 12 today, and then we could, because I don't think we'll have time to finish it, but we could finish chapter 12 on Wednesday, and then have a review during the rest of class on Wednesday, and then we wouldn't need to meet on Friday, and I would just give you the test on Friday. So that's one option. Or if you want to get out of class a little bit early today, I guess we can. We can do chapter 12 on Wednesday, and then we can have a review on Friday for an hour or so, and then give you the test. So do you like option 1 or option 2 better?
I personally like 2 because I like being able to ask questions like right before the test on the things that I've been studying but still couldn't quite get.
Okay. So that's one case for ending class right now, I guess. Is that what you're saying, Allie?
Yes.
Okay. Any other cases?
I don't necessarily mind going into chapter 12 today, but I'm with Allie. I do like a little bit of that review time just right before the test. I mean,
Okay.
It doesn't necessarily need to be an hour, but I do like some review.
So you would say combination 3, just keep going and still have a review on Friday? What do you think, Easton?
I'm good with either one. My other thought was like for option 3 is like maybe if people are still struggling with being able to find the like using the least squares method or reviewing like R square, just doing some
we could
questions in
do
class.
that today.
This is the part where the rest of the class is like, gosh dang it, why'd you suggest that?
Well, yeah, but also it's a good thing. It's a really good suggestion. So that's not a bad idea. Do you guys want to review any of finding the correlation coefficient by hand? We could maybe make the rest of time, because we've still got, what, 25 minutes left.
Well, I guess I do have a question about that. Last time you were talking about how there's like something that we can do on our calculator to help us find that easier. And it like depending on the calculator, do you know where we can go to like find how to do said thing?
Yes, YouTube. How do I find correlation on my calculator? Now, this assumes, and if you guys want to turn your cameras on and show me your calculator, say this is obviously not a calculator, but pretend it is. So, okay, Easton, yeah, Easton's can definitely do it. If you have a 4-function calculator, it won't do it. So, but if you spent probably more than $10 on your calculator, it will probably do it. And just go to YouTube. So does anybody want to turn on your camera and show me your calculator, and I can say yes, it'll do it, no, it won't do it?
I would, but my camera's not working. But I have like the TI-30XS.
Okay, so that's the same one Easton has, so yours will do it.
Sweet.
So just go to YouTube and say, how do I find the correlation coefficient on YouTube, and it will tell you. Anybody else have a question on their calculator?
I'm really sad to admit this, but I don't actually own a calculator. I just use my 48 emulator on my iPhone. So I'm going to have to go get one.
Yeah, you're going to definitely have to get one. Any other questions on that? Because you definitely need one, yeah. And a cell phone doesn't work on the test.
Yeah,
Okay, well,
I
I'm
have
going
the same
to
one as
assume,
Easton.
yeah,
Sorry, I have the same
that
one as
TI-30 definitely works. Okay, now just remember, when I write the test, the question is, because you need the correlation coefficient. I may give you the correct correlation coefficient. let me see. So normally I tell you the cheater method in Excel, but we're not doing Excel this semester. Just so that you can get the correlation coefficient correct, because if you don't, that'll mess up all your calculations. So I'll probably give you the correlation coefficient when we're doing least squares regression, because it's definitely required. But just like the homework, I want you to, well, let me show you for a second. I am still sharing, right? You can still see my Excel page. Actually, you know what? Let me show you a couple other things here. Let me back up a second. I'll make this a little bit smaller. Can you see this here? Does this look like a good example of linear correlation? This scatter plot?
No.
No. Now, the interesting thing is I'm going to do the cheater method. Correlation coefficient. And I get a correlation of 0. Would it be appropriate to say that there is no correlation between speed and miles per gallon?
No.
It would not be appropriate. That's correct. Okay. Because the scatter plot doesn't back up that 0. Clearly, you can see that this is kind of almost looks like a triangle here. It's definitely a curve. Okay. And so, so make sure that when we're doing this, that we can properly do this. But would you guys like to use the rest of today either as a review or chapter 12? Because we can't, I think it's not a bad idea. I know at the beginning of the class, we went over a few correlation coefficients, but we didn't record that. So we can do another one here.
Sounds good. Let's review.
Okay. So we'll do a review instead of chapter 12. Okay. My problem is I don't think I have any. Let me see if I can find something here in my Math 2040 class for a data set. That doesn't help. Oh, here we go. I got an idea. This is what we'll do. We're going to do a quick experiment, and we're going to find out if pulse is correlated with height. Okay, so here's what I'm going to do. I want you all to find your pulse for 15 seconds. And then I want you to tell me how tall you are. And we're going to find out and see if there is a correlation between a person's pulse rate and their height. So I'm going to tell you when to start counting here on my watch. In about 5 seconds, I'm going to tell you to start, okay? So find your pulse. I'll give you a few more seconds, and then we're going to start in just a second. Okay, and ready, set, go. Count for 15 seconds. Stop. Okay, so, Allie, what was your pulse?
17.
17. And
And
how
I'm
tall are you?
5'6".
5'3".
No,
Okay,
5'6".
5'6". So you're 66 inches tall. We're going to do this in inches. Okay, so that was Allie. How about Bridger? Bridger's not going to answer. Bridger, please answer. Interrupt me if I'm skipping you. Easton, what was your pulse rate?
15.
15. And you're how tall?
5'10".
5'10", so that's 70 inches. Okay, and then who's next? Janie, what was your pulse rate?
Mine was 20.
20.
And I'm 5'7.5".
5'7" is 67.5 inches. Okay. And Wes, what was your pulse rate?
Mine was 14.
14.
75.
75 inches tall. You're 6'3".
Yes, sir.
Okay. And Yami, what was your pulse rate?
16, and I'm 5'6".
5'6", so you're 66 inches tall. Okay. So if I give you the formula sheet, I don't know where the formula sheet is. Here it is. So you've got this formula. You'll have this for the test. So the first question, okay, we're actually going to do two things. Hopefully we have enough time. We're going to find the correlation coefficient, and then we're going to find the regression equation. So how do I do this? You're all going to have to take a step. So Easton's first. He goes, I want the easy step. So say it again.
You find the mean and the standard deviation for each
and the standard
data.
deviation. So that was good for you to answer quickly because you got the easy question. Okay, so the mean is 8, almost 69, and 16. And the standard deviation is, remember it's always .s on these, 3.78 inches and 2.3 beats per 15 seconds. Okay, so actually there was a step that we forgot. We already jumped to there. What was the step we forgot to do?
Make a scatter plot?
Make a scatter plot. That was Janie, or was that Allie?
That was me. There's Allie.
Okay, you guys' voices sound too similar. Insert scatter plot, because I don't like to take forever. What do you think of that?
It's not going to be good correlation.
Probably not good, but if you were to say it was linear, what would you say?
Linear negative?
Negative correlation. Okay, so this is a good example of a negative correlation, which actually that is true. Smaller people should have higher heart rates than larger people. Did you know that? Little birds, so a human is generally 60 to 100 beats per minute. Like little birds, their beats can be like 200 beats per minute, and an elephant can be like 40 beats per minute. It's crazy how that works, but it is negatively correlated. So we are kind of seeing that pattern, but once again, our sample size is ridiculously small. Wonder what happened to everybody else. Let's see here. So they're not going to get full points today for not sticking around. Okay, so first step was find your scatter plot. You need to label it properly. These are beats per 15 seconds. This is height in inches. This is your math, 1040 class. Okay. All right, so Allie and Easton answered the first two steps. What is the third step? Somebody else. And remember, if you don't speak up, then you get the harder questions. Or I start picking on you.
At this point, you want to find your z-score?
All right, thank you, Wes. We need to find the z-score for the pulse and the z-score for the height. Can you help me do that, Wes?
Sure can. You'll want to take your pulse of 17 minus your mean.
Don't forget your parenthesis.
Yeah. Minus your
minus
16.4.
16.4.
And divide that by your standard deviation.
Okay. We'll copy that down. And the same thing with your height. We'll let somebody else besides Wes do that. I want to move this out of the way. Who can help me find the z-score besides Wes that I haven't picked on for this?
Would you do the same, just parentheses 66?
Only if you tell me your name. Was that Janie?
Oh, Yami. Sorry.
Yami. Oh, that's Yami. Thank you. So 66 minus what?
The mean.
Which is?
68.9.
8.9.
Parentheses. Standard deviation 3.78.
Perfect. Thank you, Yami. Okay. What's our next step?
Don't we find the sum of all of them?
That must be Janie.
That is Janie.
Janie, you missed a step.
Oh, shoot.
The sum is the step after that.
I don't know.
What are we doing with our z-scores according to my formula?
Oh, we're multiplying them.
That's right. We're going to multiply them first. Okay. So we're going to multiply that number times that number. We're going to copy that down. Then we're going to find our sum. What's the next step? Who haven't I picked on? I haven't picked on Bridger, but Bridger never answers. Okay, Allie, take it away.
So after you do the sum, then you would take, it's that divided by the number minus 1, right?
Yes, n minus 1.
Mm-hmm.
And I in this case?
So this is how we're doing it in Excel, but when we're doing this by hand, you said you wanted us to round all of them to like the 4th decimal places?
Yes.
Okay, just double checking.
Yeah. Yeah, it's a pain, but yeah, just write them down, I guess. The other thing that I do want to mention is while I don't expect you guys to write down the data on the test we're talking about, because this is definitely going to be a show your work kind of a question. I'll be like, find the correlation coefficient on this data set. I would expect you to write down the means and the standard deviations rounded to 4 decimal points, although obviously you don't need to round it to 4 on those. But so please show me your mean, your standard deviation, show me your z-scores. I know the homework didn't force you to show the z-scores, but I would like to see those. And then show me the products where you're multiplying them and the sum, and then divide by, what are we dividing by in this case?
5 minus 1, which is 4.
4, okay. So negative 0.626, okay? So, and then if you can circle that or something, make sure that it's easy for me to find. Okay, so we found the correlation coefficient. Now, can we find the regression equation for this? And then actually I'm going to add another thing. Find the, is it a good model? So based on a correlation coefficient of negative 0.62, actually, well, I'm going to throw another question at you. Allie just answered that one, so we're going to throw this one at Easton, sorry. Easton, is that strong, moderate, weak, no correlation?
It'd be moderate.
We would call that moderate correlation, okay? All right, so now, now that we've done that, can we find the regression equation? So I will once again give you the equations here. Oops. Did I say? Paste. So you'll have these. There we go. And here. Oh, that looks a little funny. I don't know why. Oh, there we go. I made it bigger. That word didn't belong. Okay, so after Easton, it must be Janie's turn. What would I do to find the regression equation first?
Oh, I know this.
Remember, you got, whoops, didn't mean to move that one over. You got these two equations here for help.
Yeah, so do we find the slope first?
So let's find the slope first. The slope, which we're going to call m. How do we do that?
We take the correlation coefficient and we multiply it.
Which is negative 0.62. Multiply it by?
The standard deviation of x, which was 2.30, right?
No, standard deviation of y.
Oh, you're right. Yeah, sorry.
Yep.
And 3.78.
Okay, divided by?
2.30.
2.3, yeah. The order matters big time on this one, okay? All right, so our slope is negative 1.0283. And then, that was Janie. Wes, what do we do next?
Now we'll go ahead and take the R, your R number, which would be negative 0.626 by, I have no idea.
Okay, so we just did
okay.
that.
Yeah, I got it now. The standard deviation of your pulse over the standard deviation of your height.
Okay, so you just repeated what Janie did.
Okay.
So we've already found M. So now we need to find B, right?
That's the mean of Y, which is the height.
Mean of the height, which is 68.9.
Minus the slope of the mean of pulse.
And what's the slope?
The slope is a negative 1.0283.
Okay. Times
the 16.4.
16.4 of the pulse. Okay. So we've just found the slope and the y-intercept, and then what is the equation, Yami?
The equation. I'm not sure.
Okay, so the equation is of the form y equals mx plus b. So you just have to plug in the m and the b.
Oh, cool. Negative 1.02.
So y equals negative 1.0283.
83. Is it minus 85?
X. Don't forget the x.
X.
Okay.
85.76.
Plus 85.76415. Okay. Does that make sense? Yami, are you going to ace my test on Friday on this?
I think so. I'm writing down all the steps. It looks like there's about 8 of them. But...
Okay. Now we have to ask if it's a good model. Is this a good model? Maybe I shouldn't ask it that way. Let's ask it this. What percent of variation is explained by this model? I'll ask that question. And I have to go back to Ali again because it's your turn.
All right, I'm slightly confused by the wording on that. When we're talking about the percent, are we just talking about like if we like plugged in one of the x's to see if it would actually fall into what we think it was going to be, or what exactly are we looking for there?
Okay, so good question. Who knows the answer?
Are we looking for the r-squared value?
We're looking for the r-squared value. That's exactly what we're looking for. So how would you find that, Easton?
Just square the r value.
Yeah, we're going to take that negative 0.62 and we are going to square it. So what percent of the variation is explained by this model, Ali, now that you see that number there?
39%.
39% of the variation. 39% of variation is explained. So would you say that's a good model?
No, because it's kind of low.
Yeah. So let's think about this for a second, though. We're just trying to say that pulse is your explanatory variable for your height. What might be some other things that would affect a person's height besides your pulse rate?
Gender.
Gender might. What are some lurking variables you can think of? That's probably a better way to say it. What are some, so if 39% is explained, 61% is unexplained. So gender might be something that would explain your heart rate. What else?
So explaining why the heart rate might be different. It's like different health conditions.
Health conditions.
Healthy people have a lower heart rate on general.
Yeah, people who exercise might be an explanation for heart rate.
Could it go as simple as if someone's actually sitting down, if they just ran, walked?
Oh, that's a good thing. Are y'all sitting down or standing up? That would probably have an impact. Yeah, so there's a lot of other stuff. Plus, Well, plus we've got a very small sample size, but we did that just because there's not very many people left. But yeah, so there's a lot of lurking variables that might explain this. So yeah, I wouldn't say, I mean, we said there's a moderate correlation, but even a moderate correlation, you can see that's less than 50%. So yeah. So probably not the best model for explaining a person's height. Okay. Also interesting, this is probably one of our first things that we found with a negative correlation, but it is generally true that bigger people have lower heart rates than smaller people. I don't know why that is, but that's what it is. So,
kind of off topic, just curious. Do you
okay.
know, do taller people have a higher or lower blood pressure?
I don't know.
If they have like a lower heart rate, do they have a different blood pressure? So
I do not know the answer to that question, so we'll have to Google it. All right. Okay, we're out of time. Do you guys want a copy of this spreadsheet?
Yes, please.
Okay. I will post this spreadsheet after class today, and then quiz will be on chapter 5 due Wednesday morning, and chapter 5 homework will be due then as well. We'll do chapter 12 on Wednesday. We'll review Friday. We'll have our test Friday. It will be just like last time, where we'll do the test right after the review. Okay? So do as well as you did on the first test. This will be a little bit harder though. Every test gets harder. All right. That's because y'all get smarter. We got to make them harder. Okay, we'll see you all on Wednesday. Thanks, everybody.